Hey everybody, this is Kevin Jernigan. I'm the Principal Product Manager for Amazon Aurora. And today we're going to talk about Postgres options on AWS, options in terms of how to deploy and use Postgres in AWS. And so we'll first talk about the different managed Postgres options and covering, RDS and Aurora and a couple other facets of that. And we'll go into more details on how you actually deploy Postgres in those environments. And of course, dive deep into security and how you monitor and manage your Postgres instances in AWS. And then we're going to go through a detailed example of building an application on a managed Postgres environment in AWS. Now, RDS, Relational Database Service, is the AWS managed database service that we launched back in 2009. And today it provides support for 7 different engines. The 2 Aurora engines, Aurora MySQL and Aurora Postgres, plus 3 open source engines, MySQL, Postgres, and MariaDB, and 2 commercial engines, SQL Server and Oracle. And the goal of RDS is to make it easy for you as a customer to manage your databases by automating as much as possible the boring, repetitive things that you have to do yourselves when you're managing your own databases. So we automate things like deploying software and deploying patches to the operating system and to the database software. There's lots of built-in monitoring and alarms that automate failover. We do automated backups, and we make it easy for you to scale your system up and down in terms of compute size and storage. And of course, it's built with security built in from the ground up to support things like encryption at rest and in transit. And there's lots of industry programs that our services are compliant with. So those are just some of the things that you get when you start using RDS and Aurora. Now let's talk a little bit more about Postgres specifically, and why customers are interested in Postgres. And if you've been paying attention, you've probably seen in the last few years that Postgres has seen lots of growth and popularity, but it's been around for a long time. The Postgres project was actually started way back in 1986 at University of California, Berkeley, and it was first open sourced about 10 years later in the mid-90s. And a lot of the people who were involved in that original open sourcing step are still involved today in the core committers project, core committers group on the project. So in all that time, Postgres, of course, has been improved and lots of capabilities and features have been added, and it has lots of scalability built in as well. Now, one example of that is Amazon itself. So at Amazon.com, we're continuing to expand our use of Postgres. And the best, most recent example is that in the recent holiday season, late 2019, all packages shipped by Amazon worldwide were shipped using Postgres as the underlying database. So that's a pretty large scale operation, and it continues to grow, and Postgres does a great job of supporting it. Now in AWS, you have a few different options. And the vast majority of people who run Postgres are running stock Postgres, straight out of the open source community. And both RDS for Postgres and Aurora Postgres are a perfect fit for those customers. There are some customers who run, custom-built C extensions, or they might have even made modifications to the Postgres source code, or they have custom compile time parameters. And for those situations, it makes sense for customers to run it in their own self-managed environment on an EC2 instance. But most people are running Postgres, out of the standard Postgres repositories, using a standard install of Postgres, such as yum install Postgres or apt-get Postgres. And you can easily use either RDS or Aurora Postgres for those use cases, since both of those managed database services are fully compatible with Postgres. And we'll get into a little more detail on the differences between RDS and Aurora in just a couple minutes. But let's talk about managed Postgres in AWS. So first off, with managed Postgres, you of course get it provisioned, and you can get Postgres versions 9.6, 10, or 11. with more than 60 extensions supported. And that's one unique thing about Postgres is its extensibility. And we ship more than 60 of the most common extensions with both RDS for Postgres and Aurora Postgres. Now, the DBA's number one job is to ensure, of course, that you have your data. And you might use PG Backrest or other open source tools to back up your database with Postgres. And of course, you need to test your recovery to ensure your backup process is working properly. And the last thing you want is to need to recover in an emergency only to discover that your backups weren't really working right and you can't recover. So you always need to be testing your recovery. And then you need something highly available. Your applications are dependent on the database being there. So, the database needs to handle infrastructure blips. A network interface might go down or a CPU might go down, et cetera. And you need to do this without data loss. And with a relational database, when you commit a transaction, the data should always be there and should always come back the same way you committed it. And you need databases to be secure. The relational data is typically the crown jewels for your company. Your relational database will usually have your most sensitive customer data, and it has to be secure. And you need to be able to say who is supposed to be able to connect and see that data and when. And then you need to be able to manage all of this and to be able to ensure that what you set up is working properly. So we're going to go into all these aspects in more detail. But first, a little bit about RDS for Postgres and Aurora Postgres. So RDS for Postgres supports the standard Postgres community versions with all the ease of configuration and management that we've talked about. And it goes all the way back to Postgres 9.4. So we support some pretty old versions. This is because we launched RDS for Postgres in 2013 with 9.3. And then as the community releases new major versions, we add support for those versions. And we've deprecated 9.3 because the community did. So, we are deprecating the oldest versions when the community stopped supporting them. And in addition to 9.4 through 11, we also support Postgres 12 in our preview region, which lets you test it even before it's fully GA from the community. And so we're working on adding support for Postgres 12 in GA now. And then, of course, in RDS for Postgres, the way we implement high availability is by using our multi-AZ feature, which provides high availability across 2 availability zones within an AWS region. And we'll come back to that a little later. Now, Aurora Postgres has been built from the ground up to fully leverage AWS services. So instead of using EBS for storage, we've created a storage layer called Aurora Storage that's aware of the Postgres data and log formats. This allows us to offload a lot of database processing to the storage layer. Now, for each log record that the Postgres engine writes in Aurora, we actually write it to 6 storage nodes across 3 availability zones and process those log records down in the storage nodes rather than in the database nodes. This provides high durability with 6 copies across 3 AZs, high availability with the data available in 3 AZs, and performance up to 3 times faster than standard Postgres because of how much work we've offloaded from the database nodes. And then there's a third option, Aurora Postgres Serverless. Aurora Postgres Serverless currently supports Postgres 10.7, and the idea with serverless is to automatically scale up and down based upon the workload without you having to do anything. You don't have to go decide it's time to do a scale compute because my system's getting too busy. We automatically do that for you. And we also actually maintain the state of your connections when that scale event happens, so that your applications and users don't lose their connectivity to the Aurora Postgres serverless instance. They just see a very brief pause on the order of under a second while we're scaling up or down the compute infrastructure underneath the connections. And so this is a very useful approach when you have highly variable workloads where it might be busy for a few hours every day and then idle the rest of the time. And so serverless will scale up when it's busy and scale down when it's not busy, which can actually reduce your cost quite a bit. Now, we also have added support for what we call the data API in Aurora Postgres Serverless. This allows you to actually, for example, use a Lambda function to make an HTTP call to your database without having to, create a connection to the database and manage connections or use a JDBC driver from Lambda or any of that. So it makes it much easier to use your database, your relational database, in a serverless environment. So with Managed Postgres on AWS, you really have these three options. RDS for Postgres, which stays very close to community releases. And then you have Aurora Postgres, which is designed to give much higher throughput and has built-in durability and availability across 3 availability zones. And then Aurora Serverless, which can automatically scale from literally a paused instance with no compute at all, just storage, all the way up to a very large instance with up to 768 gigs of RAM, and also gives you the data API HTTP access. Now let's dive into the details of RDS for Postgres deployments. So you'll see different options and different capabilities that are available with RDS for Postgres. So first off is instance types. Now this is EC2 instance types that are available to support your RDS for Postgres workloads. And we support the T family, the M family, and the R family. And the key thing to remember here is that your choice of instance type is not set in stone. You can always scale up and down across any of these instance families anytime you need. So whatever you start with is just a starting point. But typically what we see customers use the T family for are for their smallest workloads. It might be test, developer workloads, QA workloads that aren't performance related, because these are the smallest and least expensive of the instance types that we support with RDS for Postgres. And then as you are either scaling up workloads to production or just moving stuff from test dev into production, we'll see customers either move to the M family or the R family, depending upon whether their workload needs more memory per CPU. And that really is totally dependent on the workload and the schema, and do you need the caching available with the additional memory available in the R family. And so we see customers choosing between these two instance families based upon the workload. Now, of course, you also have to think about storage, because database performance is essentially all about I/O. And so the choice of what type of storage you make will depend on latency requirements. And we offer 2 types of storage available in RDS for Postgres. One is what we call general purpose or GP2 storage, which is SSD storage and will actually auto scale all the way up to 64 terabytes. But it has the ability to burst for additional IOPS over the base level that's determined by the volume size. And then there's provisioned IOPS or IO1 storage. It's also SSD storage, also auto scales to 64 terabytes. But you can actually, with provisioned IOPS, you're pre-provisioning a certain amount of IOPS to ensure that that amount of throughput is available to your applications and to your database. And so the max you can provision IO1 storage is 80,000 IOPS. That is dependent on the instance type. So the smallest instance types can't go up to 80,000, but it generally wouldn't make sense to use a small instance type for a workload that needs 80,000 IOPS. We wouldn't have enough CPU to drive the IOPS anyway. So the choice of what type of storage really does depend on latency requirements and throughput requirements, and whether you need to pre-provision the IOPS to ensure that it's always available. Now, one thing we added recently was support for auto scaling. So both these storage types, you can now turn on auto scaling so that if you're running low on free space in your database, then we will automatically allocate more storage to the database. And so this helps you avoid obviously running out of space. So it's a cool new feature we added very recently into RDS for Postgres. Now, when you're configuring your instance, you'll need to decide whether it's for production or development use cases. Now, if it's for production, you will want to enable multi-AZ, or MultiAvailability Zone. What multi-AZ does is it does synchronous replication from the primary RDS Postgres database to another Postgres database in another availability zone in the same region. And it does it synchronously so that there's no data loss on a failure or a failover. And what happens is the standby, on a failover, the standby will be promoted to be the new primary with all committed changes available. And then we will actually automatically create another, with synchronous replication, a new standby to ensure that you still have multi-AZ available. And the idea here is your applications will automatically reconnect because we will remap the DNS name they're using to connect to their Postgres instance. We'll remap it to the new primary. So that automatically, all of that automatically happens when there's a failure in the primary. We will just do automatic failover and automatic reconnect of your applications. All right, so let's talk about backups. By default in RDS Postgres, we will set up backups for 7 days retention. But you should really make it longer, 14 or 21 days, because we've seen many instances when customers need to, go back in time to see changes that were made more than 7 days in the past. And so, the default is 7, but you can extend it all the way out to 35 days if you like. Now with multi-AZ, we actually take the backup from the standby. So there's literally no interference with your primary workload because we're taking the backup off the standby. With single AZ, we of course have to take the backup from the primary. There is no standby. And we'll actually briefly pause the volume to take the snapshot. And so you don't get that hiccup if you're using multi-AZ. Now, in addition to backups of the primary database, we also, of course, capture the Postgres transaction logs, the wall or write-ahead logs. So every 5 minutes, those logs are pushed to S3, and this gives you point-in-time recovery capability up to the last 5 minutes. So if you do have retention for your backup set to, say, 21 days, you can do a point-in-time restore to any point in time within those last 21 days, up to the last 5 minutes. So that's a bunch of capabilities that are just built in to RDS Postgres. All right, so security at AWS is really job zero for pretty much everything we do. So I'm going to go through a bunch of details on what's available to help you secure your databases, your RDS Postgres data and databases, and to manage authentication and access and things like that. So first off, let's talk about encryption. And so we support both encryption in transit, so SSL and TLS, and encryption at rest with KMS. And you really should turn on KMS when creating your instances. There's no real performance impact. There's no reason not to have encryption at rest enabled. So we think you should just always turn it on. And of course, after you think about encryption, both for connections and at rest, you also need to think about, well, okay, authenticating my users and auditing my users and tracking what they're doing to make sure that everybody's doing what they're supposed to be doing. And so let's talk a little about each of these layers in a little more detail. So RDS for Postgres is provisioned with SSL enabled. And this is used to encrypt network traffic from the client to the database engine. And if your client is configured to require SSL, it will work automatically with your RDS for Postgres instance. In addition to that, you can set the RDS.force SSL parameter to require all connections to use SSL. And we really think you should turn this on because then you won't, your database instance won't allow any users to connect without encryption. So, enforcing it both from the client side and the server side is ideal. Now, once you turn it on, then it's up to the client to determine what type of SSL to use and how deep it will go in verifying the connection. So there's a parameter in your connection string called SSL mode. And we think in your clients, you should set that to require. By default, Postgres says prefer, but that means it could use clear text. But you don't want to let that happen really in any scenario. So you should set SSL mode require on the client and force SSL on the database engine. And then inside of Postgres, there's a system view called pgstat SSL where you can see those connections. And basically there's a row in that view for every connection of the database. So you can see what encryption algorithms and what encryption levels they're using. So from the client side, we can go further. We can actually go and verify that we're connecting to the host that we're expecting to. Now, some organizations require verifying the host to prevent man-in-the-middle attacks. So to do that, you need to set up the certificate to support it, so it has to match the same certificate as the root. And you can download that from the RDS site. But AWS has been around for a long time, and certificates expire. And the RDS certificate is expiring in March of this year, which is coming quickly. So if you're using Postgres now, and you're using Verify CA or Verify Full for SSL mode, you need to update your certificate soon, or you won't be able to connect to your database after March 5th. So then you need to authenticate. Through RDS for Postgres, we have 3 different ways to authenticate. We have support for IAM, Identity and Access Management, and we recently released support for Kerberos, and of course, there's always the tried and true Postgres local accounts. So IAM ties in with all the rest of the IAM authentication and tokens you use throughout your other AWS services. So when you configure it, you make an API or CLI request to IAM and you get a token, which you use as a password when you connect. The token's only good for 15 minutes. It will then expire. But you need to keep in mind that for IAM authentication, there is a maximum number of connections per second, depending on your instance size. So you might need to look at connection pooling if your app requires thousands of connections per second, which is rare, but does happen. And so sometimes you will need to look at that. And so, IAM can be used, for applications that do that level of connection, that rate of connections, not just for humans who are, pointing and clicking and typing one at a time, but it just requires good connection pooling. Now, we did just recently release support for Kerberos. And if you're in an Active Directory environment, this might be the best fit. It's very fast to connect. The requirement is that your client machine must be in the same Active Directory domain. So when you set this up, you have to do this part once. You have to create a directory. You can set this up with trust between your corporate Active Directory and the AWS managed one. You do have to use the AWS managed Active Directory service. And then you set up an IAM role with privileges using the Amazon RDS Directory Service privilege. And it's possible to set up a trust forest essentially between your corporate Active Directory and the managed AD to make this all work together. For each instance where you want to use Kerberos Active Directory authentication, you'll need to connect to that directory and that role out to the database instance. So you do have to do this once per database instance. Then you'll need to add users by linking users in Active Directory to Postgres users. So we'll create a role, one that matches our Active Directory user, such as Jim at dat317.aws.reinvent.com. But keep in mind that when you're creating that role, the domain name has to be in all caps. And then for the username, the case actually matters. So if you created a username with a capital K for Kevin, you have to do it the same way here. Once you've done that, you have to grant it RDS AD privileges. Once I've connected, I still need to be able to access things. To get to my events table, for example, I need select privileges in order to query it. By default, I wouldn't be able to do that. And I might need to do a grant select on events to each user, but this can get a bit tedious. So you don't really want to be doing that. What you want to do is to create another role. And here we could create AD under our users, and you might have BI users or some other role as well, and grant select privileges to that role, and then put those individual logins, those users, into that role. Makes it a lot easier to manage. But we're going to be doing this a lot. So if you have many users across many instances, you should probably create a stored procedure to do all these steps. Otherwise, it's going to be error prone. So the first thing we're going to do is create that procedure. And it's going to take in 2 parameters, a user and a domain. And for our organization, we could default that domain to the actual domain name. We're then going to construct the full role name. So we're going to have vUser be the concatenation of pUser, the @sign, and the domain name. And we know the domain has to be uppercase, so let's make sure of that. And then we have to do good defensive programming and make sure the user isn't null. Now in Postgres, unlike in Oracle, if any part of a concatenation is null, then the whole string is null. So we don't have to check pUser and pDomain. We only need to check vUser to see if it is null. Another thing to keep in mind is that the maximum length of any object name inside of Postgres is 63 characters. So usernames, table names, view names, 63 characters. So when your Active Directory administrator is creating domain names, don't create a really long domain name and then have your usernames be first name dot last name, or you might have some users where it won't fit within those 63 characters. So then we're going to create our roles. We're going to create the role with login privileges and then grant it the RDS AD role and the AD users role. And here we're going to use a function inside of Postgres called format with the %i operator. What it does is takes a SQL identifier, and if the string that comes in needs to be double quoted, it will automatically do the double quoting for us. And then finally, we'll end that function and give it security definer rights. So for something like this, we might create using our super user account, but we might want to have other users use it, but we don't want to grant them super user privileges. So by doing security definer rights, it allows the person executing the function to run it as the user that created it. Now, for most organizations, local authentication can work just fine. If you need the high security of IAM or Kerberos, that's great, but local auth is good, fast, easy, and it just works. But there's no password complexity enforced. So we could create a user with a strong password, but once that user connects, he could come along and change that password to a weak password, violating our password complexity requirements. So we released a new feature called restricted password management. It's off by default, but when you turn it on by setting rds.restrict password commands to 1, then only members of RDS superuser or RDS password can change their passwords. So now when RPT user comes in and tries to set a weak password, that user gets an error. So this way, only restricted accounts can actually change those passwords. And that ties in perfectly with the AWS service called AWS Secrets Manager. Secrets Manager handles things like passwords and the full lifecycle of those passwords. So when you need to change those passwords on a regular schedule and enforce complexity, it handles all of that for you, essentially serving as a password vault for you, including auditing whenever you go and read that password. It will rotate your passwords on your schedule, 30, 60, 90 days, for example, and has built-in integration with RDS and Aurora Postgres. So this way, Secrets Manager will go ahead and change the password for RPT user, and for RPT user to get that password, it makes an API call to Secrets Manager, and giving a secure audited way to get those passwords, and also allowing it to be tied in with things like Lambda functions without having to put it as a configuration parameter. So when you're choosing your authentication method, you don't have to pick just one. You do have to choose between IAM and Kerberos. That's an either or, but you don't just have to pick that. Sometimes you might want to use Kerberos for humans to connect, but for service accounts on your app servers, use local authentication with Secrets Manager. Basically choose the right fit, for what you need for your application. So next we need to monitor and manage our systems to ensure they're running in the ways we expected when we first set them up. And so there's a number of different services that work hand in hand to give you visibility into your databases. And it starts with enhanced monitoring, which gives you a view into the operating system running your database. So here you can see the CPU, memory, IO, all the metrics you would expect to get at the operating system level. And all that data gets fed into and tied into CloudWatch metrics. So you can see it on a dashboard, either for an individual instance, or you can actually create custom dashboards across your entire fleet. You might have dozens or hundreds or thousands of Postgres databases, and you can create custom dashboards to see the CPU or other metrics across all of them. But metrics are only good if you can actually react off of them. So you need to set up alarms. And CloudWatch Alarms allows you to do that. If you see, for example, CPU consistently over 80%, you might want to get an email. Or if you didn't set up auto scaling for your storage and you're down to 1 gig of free storage, you probably want to know right away in order to allocate more storage before your database actually goes down. CloudWatch Alarms allows you to do all that. But we can't always predict what's going to happen in our databases using CloudWatch metrics. Lots of times what happens is, as a DBA, a user will come over and say, hey, I ran a report last Friday and it was slow. And the DBA might say, well, why didn't you tell me last Friday so I could go look? But they got busy, they didn't tell you on time, etc. With Performance Insights, if you enable it, and we really recommend you do, it allows you to look back at all the database activity for the last 7 days by default, and you can configure it to keep up to 2 years of your database activity. So with Performance Insights, you can go back to last Friday, highlight the time period in which that report was run, and drill down and see what was going on in the database at the time, and even drill down into individual await events. For this particular example, at the time of the slowness, we were running a store procedure called load events, which was doing a load into the database. And we have a wait event called wall sender main, because this database has a replica. So of course, when you're loading data, it can take a lot of time and resources to replicate all the data you're loading to the replica. So we can look at other things that were going on in the database at that time, going back a week or up to 2 years, and drill down into individual wait events that are happening, et cetera, et cetera. So Performance Insights is a really useful tool. Now, one of the coolest things we recently released is integration of your Postgres logs into CloudWatch. So Postgres writes a wealth of information into its error logs, everything from checkpoint info to syntax errors to audit info. So if you enable PG Audit, for example, to collect audit info. So let's talk about building an application. Whether you're using RDS for Postgres, Aurora Postgres, or Aurora Postgres Serverless, it's still Postgres. And so for any of these deployment options, you want to build an app that leverages Postgres features and decide which deployment option makes sense. So let's start with a simple app that loads JSON documents from S3, from an S3 bucket into the database. Now, everybody likes JSON, so this should be a good example. So let's say we have partners and customers putting JSON documents into the bucket, and we need to make that data available for users to run queries on them. So, you could trigger a Lambda function when a file hits the S3 bucket and automatically insert the file into Postgres. Now that works fine, but it's inefficient because we're moving that data twice. It would be much better to trigger a Lambda function, which would tell Postgres to load the file directly from S3. And so, the ability for Postgres to copy data directly from S3, makes it much more efficient. Now, that's actually available now with the S3 import feature. So if you had an on-premises Postgres system where you were used to using the Postgres copy command to load files directly into your Postgres databases, you can now do that in RDS for Postgres from an S3 bucket. And it's available with the AWS S3 extension, and it follows the copy syntax. And you can secure that bucket using IAM or security credentials. So if you're doing this in production, you should use IAM. And the first thing you'll do is create an IAM policy to give access to the S3 bucket. And we'll then create an IAM role for RDS to allow the RDS instance to use IAM. Then we'll attach the role to the policy. And then finally, we'll connect that role to the RDS instance. Now, again, if you're doing this in production, this is how you want to set it up. But if you just want to test S3 import, you can use security credentials in your dev environment, more like a username and password. And we have a helper function called create AWS credentials to help you with this approach. And this is all part of the S3 import function. But you got to remember, in this case, you're responsible for the key management. So let's load that data in. The first thing we want to do is put it into a staging table. Because if I'm getting data from partners or other external sources, it's just a good practice to never load it directly into the main table. You should always load it to a staging table first. Now, Postgres lets us do this to an unlogged table. This means Postgres doesn't write data to the log files for this table, so it won't get replicated to other instances, but it's of course available in the instance where we're loading it. We'll then create a stored procedure called load staging that takes 3 parameters, the region, the bucket, and the file. And the first thing we want to do is truncate the staging table to make sure there are no records left from previous loads. Then we'll load using the table import from S3 function, which has a few parameters. The first is the table we're going to load. The second is an empty string listing the columns we're loading. We don't need to list any in this case because it's just a single column. And the third parameter is the Postgres copy command options. You might want to, for example, specify different delimiters, etc. And finally, we have the location where the file is, and we have another helper function called create S3 URI, which points to the location of the file. We'll then want to load the data into our main table. So we'll have an events table, which has 2 columns, an ID of type UUID, so we generate that ID on the database side so we don't have to do it on the app server, and an event of type JSON. We know we're going to have a lot of events, so we're going to hash partition the table. Now, if you dig into it, you'll see Postgres has lots of options for partitioning. We're going to choose hash partitioning. Now, it's a lot easier to partition a table from the start rather than to take a monolithic table and partition it later. So it definitely makes sense to plan ahead for this. Now, we'll start with 2 simple hash partitions. Then we'll create 2 indexes. One is a unique index on the UUID, and the other is a GIN index, a specialized index type in Postgres, which allows us to index the entire JSON document. So we'll be able to quickly search on any element inside all the documents. Then we need to load the events table. So we'll create a procedure called load events. Now, the first thing it's going to do is call load staging. And if there are any errors, we're going to roll back. Remember, one of the first things we did was truncate the table. And one of Postgres's hidden superpowers is that commands like truncate can be rolled back. They are transactional. So if there's an error, anything we truncated will actually be recovered during the rollback. Then we'll load each of the rows. And we'll first scrub the JSON. And we'll get into details on what that means in a moment. But if scrub JSON returns null, we'll put it into a bad record table and come back later to analyze what happened. Otherwise, we'll put it into the main events table. So the scrub JSON function takes a text string and returns a JSON record. Now, let's assume our partner didn't really understand JSON, so they use single quotes around all the elements when they should have used double quotes, and that's not valid JSON. So in this function, we're able to replace the single quotes with double quotes. And then we'll parse that JSON, and if there's some sort of error, we'll catch that and return null. Now, you might notice that this is in a different language than the other code I've shown you. This is in JavaScript. And Postgres has support for multiple stored procedure languages. And so here we can do it in PLv8. And when you're dealing with JSON docs, JavaScript works extremely well. When you catch the exception in here, it's more efficient, for example. In standard Postgres stored procedures in PLPG-SQL, Postgres uses sub-transactions to track exceptions, which are very heavyweight operations. So by doing the exception handling inside of PLv8, it uses the PLv8 engine for exceptions, which is much more efficient. In this example, gave about 20% performance improvements. And so, there are support in RDS Postgres for these different types of languages. And we generally see most procedural language being written in PLPG-SQL or JavaScript with PLv8, but we do support these other languages as well. And really, it's all about choosing the right tool for the job based upon what you're trying to do in your code. Okay, and so then when you're querying the data, Postgres has support for parallel query. Because as your database gets bigger and bigger, you want to be able to leverage multiple cores to query, that larger data set. And so Postgres Parallel Query supports parallel scans and joins and aggregations and appends and new versions that keep on adding support for more things. But this works even to the point where doing a select count star from the events table, we'll do a parallel index only scan. So there's lots of cool stuff in Postgres parallel query as well. But we're dealing with JSON data, and actually available in PG12 is support for JSON Path. So traditionally, to query a JSON document, we had to compare it with snippets. So if we wanted to find events, say from July 16th, 1969, we had to compare it with a JSON document. It's not very intuitive what that means. So you can see here you have this @ sign, which means contains, and it works, and it's extremely flexible and robust, but it's not very intuitive. But the SQL 2016 spec gives us the ability to do this in a different way, and it's available in PG12 now. So now you can use the JSON path, and you don't have to create it as a subdocument. So it's a lot easier to tell what's going on with this syntax. Another cool feature in PG12 is generated columns. If we have an event doc, we're always searching by date, say often by date range, and you have to do that over and over on large JSON documents. That can get really expensive. So ideally, you'd be able to pull that out of the JSON doc itself. Now, we could do that with triggers, but they're pretty heavyweight. And generated columns lets us do that much more efficiently. And you do that by creating a generated column based on other columns in the data itself. And this is useful when you'll be frequently querying off of the generated column with significantly less overhead than using a trigger. So that getDate function will just call that same JSON path query in order to get the date out. And here we're using a SQL function instead of a PLPG SQL function. So if you have a simple function that boils down to a single statement like this, you should really do it as a SQL function, because Postgres will handle it at the parser rather than the executor level, making it behave more like a macro and giving significantly better performance. So taking a step back, just a few things to remember here. When you're setting up your Postgres instances, you should turn on MultiAZ for your production workloads. You should enable backups longer than the default 7 days. You should both turn on SSL and force SSL on the connections. And you should have a strong password regimen. You should also definitely turn on automatic minor version upgrades. And when you're building applications, take advantage of Postgres syntax. Don't just stick to select, insert, update, delete. There's a ton of really great features in Postgres that will help with your application development. Specialized data types, specialized functions, etc. You should really use all of those things. So thank you for your time. We look forward to helping you adopt RDS for Postgres and Aurora Postgres for your applications. And I'm going to stick around and take a few questions now in the chat. Appreciate your time. Thanks.